Very good. Thank you so much. And thank you so much, Jose, for helping me set up everything on the GPU server that you have, so that everyone can contribute today and start working with your homework for this session. By the way, you're still sharing your screen, so you can possibly stop sharing. Perfect. Okay, so welcome back, everyone. We're going to continue from yesterday. And yesterday, if you remember what we did, we had a set of things we went through. We went through, I have my cheat list here. We went through a short introduction about the course. We had the Hello World in Jupyter notebooks with Python. And then we started using the GPU and added PyCuda to the mix, and saw how we could actually run some computations on the GPU through the high-level Python language, which I thought was very nice. And we got so much work done yesterday with the Monte Carlo integration and so on. And you may remember something like this, where we had the I'm sorry. I have to fix the camera so that it has the right zoom. Let me see. So it's going to be there. Should be better. Okay. So we went through this yesterday, essentially looking at numerical integration and how Monte Carlo integration could be an alternative. And then we used the Monte Carlo integration to try to estimate the area of a circle by throwing these darts. Okay, so we threw all of the darts into the circle, and we estimated that the area of one of these darts was a certain amount, and then counted the number of darts inside each section, inside or outside the circle. And then from that we could estimate pi as this formula down here: 4 times the number of points inside divided by the total number of points we threw. I would actually like us to finish off that subject. I ended off yesterday with a small bug. Essentially, there was something wrong with my implementation, and we got an error message towards the end of the day yesterday. So right now, I'd like to continue a bit with that. So it's spent some part of the start of this lecture just finishing off the computation of pi. And what we did there was some instructional things. We started with a simple example that worked in one case, and then we made it work with more darts and more efficient. So we're going to go with a couple of more optimization steps here. And once we're done with that, where did my cheat sheet go? There it went. Then I thought we would go through some best practices for high-performance computing. And this is really important, because once you're developing source code, and this is not only for high-performance computing, I'm assuming that all of you will have something to do with computing in your careers. You'll work with computers somehow. And by doing that, you need to do it following best practices, essentially. So we'll go through that, and that's going to be helpful for you. Perhaps not today, but I promise you, if you follow the guidelines that I give you today, it's going to be useful for you for the next 10 years. Then we'll go into this sort of the diamond in this lecture series, which is the hyperbolic conservation laws for me. So we're going to do some numerical simulation in Python with CUDA, and hopefully we will all be able to run all of our examples, which is also part of your homework. So you're going to have homework, if you look at the webpage, which is going to be to do some of the things that we're going to do today, but also write a report about it. So this also comes in your in the learning digital learning platform that you have, which Jose, I'm lucky that he helps me publish things there. Okay, but let's start off with the example from yesterday, the Monte Carlo simulation. Are there any questions? Anything you wondered about? Why did he do that from yesterday? Or comments? Okay, no comments, no. I think we need to do the same exercise we did yesterday. So I'm going to say hello to you all, guys, to warm up our voices. Good afternoon, Luis Miguel.
Hello.
Hello. Good afternoon, Daniel.
Good afternoon.
Good afternoon, Pedro.
Good afternoon, bro.
Good afternoon, Adrian.
Hi, good afternoon.
Do you use both names, Adrian Mora, or is Mora a last name?
Adrian.
Adrian. Excellent. And good afternoon, Alfonso.
Hi, good afternoon.
Very good. Then I know you're all there. It's much better for me. And as I said yesterday, please keep this interactive. If you see me doing mistakes, interrupt me, and I will we'll have a discussion. I think that's better for you, and it's definitely better for me to get some feedback from you. Okay, so let me see if this works. Good. This is where we were yesterday. And I've cleaned up the source code a bit. And I will actually make the source code available for all of you guys on GitHub so that you can view it there and review it after the lectures. So I'm going to do a kernel restart and clear all outputs just to make sure that we're on a clean slate. Okay. The first thing we did yesterday was to import some packages, NumPy and matplotlib for plotting, and then time to be able to check how long time a certain statement would take. Then I imported CUDA through PyCuda, so the package which is here. And I included the functions in CUDA, the source module to help me compile the kernel sources, and auto init to just initialize the GPU for me. Then I created this CPU function to generate some random numbers. Okay? And this is just regular Python. Created the random X numbers, the random Y numbers, and then I did something a bit different yesterday. I created this statement here. Inside is numpy square root x squared plus y squared. That's this statement here. Less than or equal to 1. So by entering this into my source code, I will get an array which looks something like this. So it's going to be 0, 1, 1, 0, 0, 1, 1. So it doesn't have the radius or the distance from the origin anymore, but it has the 0 or 1, depending on if it's inside the circle or outside the circle. And by doing that, I can quite easily compute the sum by doing numpy sum to count the number of points inside. And then I just compute pi as that. And by doing that, this small fix here, by doing this compared to what I did yesterday, improves the performance quite a bit. So that was the reason I did it. And that's to make it a bit more fair when we're comparing the CPU versus the GPU. Okay, so I did 512 million samples, just throwing 512 million darts. And then after 15 seconds, it should give me an estimate of 3.1416, which is close enough. The true value is 3.1459. So it's about right. And then we created the GPU kernel. And what we did there is that we had the shared memory, which was one of the optimizations we did. And what I've done since yesterday is I've added some parameters that we didn't have time to do yesterday. So I added the number of iterations. That's the for loop, you may remember. And I added a seed. And this is an important thing I overlooked yesterday. I'll come back to it. Okay, but the shared memory was an optimization which made that we could reduce the amount of memory transferred between the GPU and the CPU by a factor of 512. Because now, instead of each thread writing a 0 or 1 to memory, we would have the whole block, which consists of 512 threads. Just one of the threads is going to write to memory. So it's just you just reduce 512 elements into the single sum. And then we did the other one, which is to have the for loop so that each thread throws more than one dart, right? Originally, each thread would just throw one dart, finished. But now we would say, well, let's do 1,000 darts per thread. And that also increases the number of calculations in relation to the memory transfer. So we're transferring less memory because each thread is calculating more things before writing to memory. And inside here, it's exactly the same. The one thing about the seed that I mentioned, this seed in here, that's important because we're using this strange random number function. We're using this thing up here based on Bjarne Strostrup's pseudo-random number generator, which has to have an initial value, this last draw. So it generates a sequence of random numbers, but you need to have a first random number. And originally we were using the thread ID as the initial random number, but that means that every single block is going to have the thread ID 0 to 512, which means that it's not actually going to give us more random numbers by having more blocks, because each random block is going to give, or each block is going to give the exact same random numbers. So that's like a small thing that we need to be aware of here. So what I've done is I've changed the seed so that's the specific thread ID in the whole domain plus an initial seed. Okay, then we had the shared memory reduction, which went from 512 elements down to the single one, and we wrote that out to memory. Are you all on board so far? Just give me a thumbs up if so. Okay, I got one thumb up. Oh yeah, good. You found the thumbs up. Excellent. Great. And as I said, interrupt me if I'm going too fast or too slow or something. Then we created this Python function to call the GPU kernel. So the GPU kernel is up here, and we're calling it from down here. We had some discussions about the allocation, making sure that we allocated the same amount of bytes we needed on the GPU as we had on the CPU, and making sure that the data types are also the same. So if we were using single precision on the GPU, we have to use single precision on the CPU. If you're using unsigned int on the CPU, use unsigned int on the GPU. So also always make sure it's identical, that it's symmetrical. We had some calculations related to the number of blocks and so on, and this is actually where I had the mistake yesterday. I forgot to divide by iterations per thread. So I added that in secrecy whilst we were offline, and I got it to work. And now, by running this, I've added some more comments here, but now we can run a very large number of darts. So this is, let me just say, that's 1,000, 1,000,000, 100,000,000. So that's 51 billion. Is that right? So let's, if we just add, so this is 51 billion 200 million. Oh, it's even more. It's a huge number of darts. But how long does it really take? It takes 2 seconds for it to actually compute this. And now I've given it 2 parameters. So each thread in CUDA is doing something like, is it 10 million? Yeah, it's 10 million darts. So each thread throws 10 million darts. So the for loop, which I mentioned up here, if we go up here, this for loop where we generate the random numbers, it runs 10 million times. And I'm using 512 threads per block. So this is very, very fast. So far, we've had a huge reduction in time compared to the CPU, and especially compared to our original GPU version. But still, there are some things we can pursue with this. And one thing I would like to do is to look at the overheads related to a function call in Python. If you remember from yesterday, I said that for loops were kind of slow. So here, in the Python function, right, this is the CPU version, I would use this statement, but I could have done something like for I in range endpoints inside n inside is equal to plus equals, and then this statement here, but with indices, right? So I'm going to do x rand I, y rand I, something like this. So these two statements, they are the same, but one takes a huge amount of more time. So let me demonstrate for you. Let me just get something which is kind of reasonable up here. So now I commented out, so now I'm using the for loop approach. Then I have to do, okay, so I have to do it a bit different. N inside is equal to 0. Okay, so I start with 0 and then I just count up. It saves a bit of memory, but this is really slow. So I comment out these things here, and then I'm going to run it, and I'm going to run it for 512,000. That takes 1.84 seconds. Okay, so let's just note down that. For loop, 1.84 seconds. And let me run it once more so that we see that it takes about 1.84 seconds. It's like repeatable for 512 elements. Okay, now let's change the source code. Let's make this, we comment those in and comment these out. Okay? And I run it again. Same for 512,000 elements. Vectorized 0.023.
What is it doing, Python, in behind?
Excuse me, what did you say?
I mean, how is Python processing the numbers in that case to be more efficient?
Very good question, right? So you see, this is like a factor 100. 100 times faster, right? It's about 118, so it's 100 times faster. Now, what's going on behind the scenes here is that for this vectorized thing, this thing here, that actually uses the whole vector and sends it to a C++ library, and the calculation, the for loop, is run in C++. And then you return to Python and say, I'm done. But for the other one, for this one, where you have the for loop inside of Python, then Python has to execute every single statement. And that's really, really slow. So executing things in Python is really slow. And that's one thing to be aware of. So when people say that Python is slow, they're absolutely right. But I'm saying that Python can be really fast. If it can be 100 times faster if you know what you're doing. So you need to make sure that you actually use vectorized notation and so on. And then you get very close to the C++ performance. Because this statement here has very little overhead. Now, I was talking about overheads. Does that answer your question, Luis Miguel?
Yeah.
Good. So, what I was talking about overheads here, right? I was saying that using for loops is slow. If we go down into our source code and look at the thing down here. Oh, sorry, it jumped for me. This one down here. This calls a GPU function, but it calls it from the CPU, from Python. And this has a lot of overhead. So we can make this more efficient. And this is especially important if we're going to call this kernel multiple times. Right now we're just going to call it once, so it's not really going to affect our performance. But what we're going to see later today is that we have one kernel being run every time step. So we're going to run a kernel millions of times. And then it's really important to, if you reduce the time it takes to launch a kernel, then you're multiplying the cost of that by 1,000,000 times. So if you can make it a bit faster and multiply that a bit faster by 1,000,000 times, it reduces your runtime of your whole program significantly. All right, so that's what we're going to do now. And that's called a prepared call. So I'm going to just open my cheat sheet, which is over here. Just going to move it a bit around on my other screen. There. And the thing about this kernel call thing here is that it has to do a lot of conversions. It has to find it has to find the location of the variables. It has to find what type of variables, set the variables, and so on. But we can give that information to Python at the beginning, so that it only does this once. And that we can do up here. So we get the function, right? And what we can do is we have the function here. So let me add a new. Oh, sorry. I tried to add a new. I added a new cell, but it jumped. So we're going to do this kernel, and I'm going to prepare this function call. And now this has a bit of strange syntax. What we have to do here, prepare a function call. Give PyCuda instructions on what type of parameters to send to CUDA. So this essentially just changes some of the responsibility from PyCuda into your own hands. So now you have to make sure that you are saying the right type of variable types in your preparation. So let's look at our function up here. This is our function. So I'm going to copy this one, and I'll keep it down here as a note to myself, right? So this is the function signature, and this has a pointer for the first one, and then it has an, oh, I forgot actually what unsigned int is. I think it's UI, but I have to double check. Prepare. There. Well, let's just guess what it is. I think it's unsigned int, unsigned int. So this, I don't want to give you the wrong instruction, but essentially I think this is right. What it says here is that the first parameter is going to be a pointer. That is this here, the star, essentially your pointer to some data. And then it's going to be an unsigned int, which corresponds to this one, unsigned int. And the same with the last one. So I have 3 parameters into my function, and that comes out as 5 letters. But it's a magic command, and let's just cross our fingers and hope this works. Okay, it seems to have worked okay, but we're not going to know until we actually run the kernel. By preparing the kernel, we can, instead of doing this this thing over here where we give the variables in this way, we can do a compute py GPU kernel prepared call. And now the variables change a bit in their location in the call. So I'm going to copy these ones so that I have threads is equal to that and grid is equal to that. Okay, I've defined my block, I've defined my grid, and the prepared call takes in the arguments in a similar way. Grid, block, and then come all of the other arguments. So it's going to be inside GPU, numpy, uint. I'm just going to copy this again.
What does the P stands for? I mean, the P that you have put in the other parameter. It was P, UI, UI.
So here, the P?
Yeah, that one.
Yeah, so if we look at this...
It's like that they are pointers.
Yes, pointer, exactly.
Okay. But
So,
in that case, there is another UI missing, right? Because you have 3 variables.
I have 3 variables. So this one, this is pointer.
Okay.
This one is unsigned int, and this one is unsigned int. That should be let's see if this works, but that's that's what I'm. It should be more or less right. So then we had the prepared call, and you see it's essentially the same as the function above. But the difference here is that now we've told Python already that I know what kind of arguments I'm going to use. Please optimize so that this works efficiently every time, so you don't have to check anything. Other than that, everything else stays the same. And I should be able to run it, and it crashes. Bad character in struct format. So that relates to this this here. So I'm gonna do it maybe just the eyes, so it doesn't care about the unsigned, and let's see if it runs. Okay, it runs at least. Okay, so I made a mistake there. It was not unsigned int. I think it's the I. I'll double check this and make sure that I comment this correctly when I give you the actual source code, the Python notebook. Okay, so let's run this a couple of times and see what happens, right? We were using 2.16 seconds, and it doesn't really change too much. And as I said, this is because we're running the kernel just a single time. If we run it multiple times, that's where we get the true benefit. Okay, so this one, no benefit right now. We run the kernel only once. And this is often the case. You try out some optimization techniques, and it doesn't give you any benefit. And sometimes it actually gives you a performance downgrade. So your kernel runs slower, or your program runs slower. You try to make it faster, but it runs slower. And if I look at my code now, it has this extra prepared call, which is kind of more confusing. So I'll come back to that in the best practices. But think about this. It didn't give me any performance gain. It made my code more complex and difficult to read. So does it really make sense to have it there? I think no. I think we should just remove it and keep back with the old one, which was working well and was as efficient as it needed to be. Okay, another thing we can do here is to do a sum or reduction on the GPU. So far, we've reduced so that we have shared memory to reduce the number of elements written per thread. So now each thread doesn't write anything, but each block writes something. But still, we may have a very large number of blocks, right? Let's say we have 100,000 blocks. We can reduce this to on the GPU by doing a reduction in memory there to the single sum of number of inside. So we can actually perform this calculation on the GPU. That means moving this calculation onto the GPU. So this is version 6 move this reduction to the GPU and only transfer a single number to the CPU. That's the most efficient we can do. That's actually very efficient. So this would be my next approach to make this application faster. But that's going to take a bit of time. So I think I'm going to skip that and focus on other parts of the lecture material. But this is how we can continue by optimizing performance, right? So we had this version 6. What's next? Version 7. What should we try there? And at some point we need to do profile-driven development. Profile-driven development is something which is really important. Right now I've just been following my gut feeling. What are things that I think are important that will reduce the time it takes to compute pi? But to really know what's taking time and get some pointers, I should use profile-driven development to get profiling results telling me that this exact thing is the thing that takes too much time. So that's what lies in the future of optimizing this. But it's a bit too advanced for what we have time for today. There are slides on my webpage which cover some of this, so you can look at those. But let's leave this now. Is that okay? Good. Any questions to this so far? Okay, no question. Then I think we can move on. Okay. What I would like to do then. So so far, excuse me. So far, we've been looking into the computing pi. Oh, my throat is okay. I have to get some water. Sorry, guys. Give me 3 minutes, and I'll be back. Okay.
No worries.
Hola. Por favor, los que estáis, ¿hay alguno conectado a ILEX?
Yo.
Ok. Perfecto.
But I can quit if it is necessary. Okay.
Really sorry about that. It's yeah, my throat was you know when you have a cough just irritating your throat and you try to suppress it, it just gets worse and worse and worse. So
No worries.
good. Thank you.
It would be much worse if you lose your voice. So,
Yeah. So we were using we're looking into computing pi so far. We looked at how that could be a way of doing like Monte Carlo simulation, how we could improve performance of GPU code in versions. So we started with one version, optimizing it further on. And now I'd like to go through a slide set with you, which is on best practices for high performance computing. And let me see if I can find the slide sets there. It was here just a minute ago and now it's gone, but there it is. Good. And let's see if this works. Just give me one moment. Yes, I think it works. Good. So this is actually, I think not the only, we're going to have a bit of slides today with this section and something with the hyperbolic conservation laws. But here, with this conservation laws on GPUs, best practices, what I want to go through with you is writing scientific software in a good way. And this is not only scientific software, this goes for all software. So it's going to have a bit of some examples and some best practices and yeah, essentially some best practices. Okay. Yeah, so this is one of the references which has a lot of good topics on this. So it's from Greg Wilson, Best Practices for Scientific Computing. It's available online. Now, I want to start off with, as you see the weapon there, the Kalashnikov. And then above me, the Blackbird bomber. Why I have photos of these two things in this section is because these were designed under very specific principles. And I think we should design our source code in the same way. The Blackbird aircraft, which is up here, that was actually designed at Skunkworks, and they were given the task that the lead designer came up with a table. On the table, he puts standard equipment that you would have at any airport. Sort of any local small airport, you would have this equipment. So there was no special equipment there. And he said, I want you to design this supersonic bomber for me, but you cannot use any special tools. You have to use the tools which are here. And if you look at the Kalashnikov, which is hidden behind me, that's the world's perhaps most iconic rifle. It's an automatic rifle, so it's like a machine gun. And you've seen it in movies, you've seen it everywhere. This is like the classic terrorist gun. It's you can see it in the countryside. Why do you see this gun and not other guns? And one of the big reasons for this is that this gun is very easy to repair. You can take it to a local blacksmith and he can most likely repair it because it is built very simple. It's a very simple mechanism. It's not the most accurate gun. It's not the most best gun in many ways, but it is the most repairable gun. It's very easy to repair. It's very easy to produce. And I think like these are a bit, I'm more towards pacifism than towards military myself, but these are good design principles. You should design things that are easy to maintain by others. And when you write code, you shouldn't write code which is highly sophisticated. You recall that I just talked about this prepared call, which we added into our source code for the Monte Carlo simulation. And then I said, well, perhaps we should remove it again because it didn't give any benefit, and it's actually a kind of a complex technique. You need to. I didn't even remember that it was PII. I thought it was PUI. So I even forgot some of the details here. So this was sophisticated machinery, and if we don't need it, we shouldn't really use it there. So a pitfall that I often see with a lot of students, including myself, is that I try to make things advanced and able to solve everything, right? I try to make this, if I were to make this this rifle here, I would make this rifle also be able to work like a hammer and perhaps a screwdriver, and it would look like a Swiss Army knife. And it's kind of useless at all the things that I designed it to do. So think about it. When you design something, try to keep it simple, keep it stupid, and make one program to solve one task. You don't need to write the huge, big program to solve all problems for all future. And then, number 2, use a high-level language. In this course, you're mostly using C or C++, and I'm coming in with Python. And I think that's a very good thing. If you look at the things that we've been able to do right now, I didn't copy, well, I copied a bit of code for the shared memory reduction. But other than that, I wrote more or less all of the codes live for you. So in less than an hour, we could do some quite advanced Monte Carlo simulations on the GPU by using Python. So that was very, I think that would not have been possible for me by using C++, for example. Also, write programs for people. Never write programs for computers. This ties into one of the following best practices as well. When you're writing code, write it for the next student who comes in and is going to work on your code. How many of you have looked at someone else's code? Worked with someone else's code?
That's my case.
Yeah.
Not here, but
So how did you look at the source code? How was it easy to work with someone else's code?
it depends. I mean, now that I'm working in a professional company, it is easy because people make it to make it easy to read. But in college, for example, it was a bit more difficult to read.
That's a very good point. And Jose Manuel, welcome. By the way, I saw you come in here.
Hello.
Hello. We're in a slideshow about best practices, and I think this is really important. Even though you're not going to necessarily use it today, this is important for you for your career. It's going to be really important for you for the next 10 years and the rest of your career. But Luis Miguel, you said something important. Now you work with industry, and it's much easier because they try to write good code. If you write good code, you're more likely to be hired by a good company. Just if you can write good code and show it on GitHub, this is my code, it's nice, maintainable, easy to see, easy to use, everyone can actually work with this code, then they will see that, wow, perfect, this guy can come into my team, be really productive with all of the other people on my team, and it's just perfect. But if you write spaghetti code, which is just a nightmare, and you're the only one who can work with it, it's then you have to be retrained to be able to do this in a more maintainable way for other people as well. So this is actually a thing you can do for your own career. Write a project in your studies, make sure that it's available on GitHub, and make sure it's easily readable code. Then you can add it to your resume when you're applying to jobs and say, hey, look at this code. I wrote it. It's very good. Luis Miguel, you shared also a link here, refactoring.guru. Sort of refactoring, I totally support that. So I haven't seen this link myself, but yeah, I'll check it out later. Okay, is this useful for you guys, by the way? Nobody says yes?
Can you repeat the question? I didn't.
So, is it useful to hear some of these tips, do you think?
Oh, yes, it is.
It's based on course.
I hope it's useful, and I hope it's yeah. That's my aim. I don't want to be like preaching sort of this is what you have to do, but these are some tips and hints. And I've done a lot of mistakes myself throughout my career, and I wish I would have done this from the start. When I was studying like you guys, I wish I was using these kinds of tools. Okay, next one. Use version control. Use Git. Use Mercurial. Use GitHub. It's perfect. Everything I do, more or less, is now versioned. It's a very good way of having a backup. It's a very good way of collaborating with others, with Git, with pull requests and so on. And it's the way that all professionals do it. So in my courses at Oslo Met, I'm actually requiring the students to use Git when they're handing in their assignments. So they have to learn how to use Git, and that's really one thing that our industry loves. When our candidates come out and they know how to use Git in a good way, they give us thumbs up and say that we like that in the candidates who come out. Use the computer to record history. This is really, really important. I guess you've worked with mandatory assignments and you've done like me. I showed you now the source code, right? I'm on the screen. The source code for the Monte Carlo, right? And I did the copying of the kernel. And I said, well, I think I may do some mistakes now, so I'll copy this. Okay, so Siri thought I was scared. So I don't know how to turn off Siri to stop listening to my voice now. She's very aggressive listening to me at the moment. So when I speak, I apologize. But I copied this text. I copied the kernel. I said, well, this is something that I may do wrong. And then I started changing things. We should use the computer to record this history through version control, but also when we run experiments. I guess in your mandatory assignments, you've done things like running programs with parameters, and then you change the parameters until you get it to work. You go to sleep, happy that it finally worked. You wake up the next morning, try to run the same experiment, and it doesn't work. Have any of you discovered that or had that feeling?
Every day.
Yes, every day, right? You say, what did I do yesterday? It worked yesterday. What did I do? Use the computer to record it. So when you're in the Linux command line, you can use the history. That will give you sort of, well, what did you do yesterday? But more importantly, also try to keep track of these things in a good way. Document it for yourself. And versions of software and data, that's really, really important. Trying to reproduce results is really challenging. So make sure that you're using the right version of the software when you're running your experiments, and write it down. Write down, I used version 3.2 for these results, and these were the parameters. Because then you can go back in time and reproduce the results you did earlier on. Good. Optimize software only after it works correctly. This is what we did with the Monte Carlo simulation. I remember when I was a student and I had I was convinced that I would write very good code and all of my code would be very efficient all the time. And now I'm getting older and I'm thinking that, well, it doesn't really help me that the program is fast if it gives the wrong result. So it's much better for me with a very slow program that gives the right result than a very fast program that gives the wrong results. So I've changed now to make things work first, like we did with the Monte Carlo one. We said that, well, we're not going to make the perfect version first. We're going to create a version that works. And then we can try to optimize it from there on. It's much easier to make a slow code fast than a wrong code right. You've been debugging for hours and hours, I'm quite certain. And it's easier to make things faster than it is to make it right when there first is a bug there. Also, write tests. This is something that haven't been covered in this course, but it's really, really important. This is also one of the cornerstones of my scientific work. And also my industrial work. I've been working in industry as well. This goes back to the thing that it worked yesterday, it doesn't work today. What happened, right? If it worked yesterday, write a test, making sure that everything is the same. It can be as simple as testing the output of your program. If the program is supposed to write out the number 5 every time, and it works correctly if it gives 5 and wrongly if it gives something else, then just make a simple test that checks that the output of the program is 5. By doing that, you have a very quick safety valve, so that if you do something wrong in your program and you run the test, it tells you, well, something's wrong. And you can then quickly act on it and say that, well, I did these things. And that ties in with the use of version control, because you can go back in time with version control and say, well, 2 days ago it worked, and now it doesn't work. Let me look at the 2 days of changes, which I have stored in Git, and try to see if I can find the bug. That's typically the way that I go through this. And testing in itself, I think that you could do a whole semester full of testing, like a 10 ECTS course with testing. So this is just a small taste of what you should look at. Test-driven development is also one keyword that sort of falls into this this line of thought as well. Okay, next one is software testing, and I'm going to hide myself again because I think this is very nice. Have any of you seen this photograph before?
Yes.
Cool. So this is actually a logbook from the Harvard Mark II from 1947. And it says here something over here. Relay number 70, panel F, moth in relay. First actual case of bug being found. So what you have there is that you were using these vacuum tubes. You've seen these glowing tubes, radio tubes. They're called in Norwegian. And bugs, like physical insects, would come into them because they're warm and short circuit them, make other things. And you would have to track through, find where the bug was. So this was the original bug. But software testing, really, really important. One of the key points of software testing is to increase the level of testing as time goes. Every time you find a bug, make a test when you fix the bug. So, well, first make a test that exposes the bug, then make sure the test succeeds, essentially removing the bug, and then continue. And by doing that, you will add more and more tests to your source code. So you don't write it all at the same time, but just write it every time you find a bug. Your program is going to be better and better and better. And this is also one thing that's really, really important in industry. So if you work with industrial level code, you'll see that people are actually using a lot of testing. That's one of the key things that they care about. Okay, regression testing. This is what I said about checking the output of your program, that it's 5 if you expect it to be 5. And if you look at the table up here, there's only one time when you should change functionality of your program, and that's when you're fixing a bug. If you're adding a feature, refactoring, or optimizing, nothing with the output of your program should change. So if you have a test which checks the output of your program and something changes and you're trying to optimize, you know that, well, I did some optimization which doesn't work. So this is, yeah, again, really important to do testing. Okay. Licenses. This is something which is incredibly important, and I think nobody really teaches anyone about it. Have you heard about license issues before?
No.
So some of you have heard about it. Very good. Can you copy code from Experts Exchange and use it for your commercial code?
If you don't have a license, no.
You're right. If it doesn't have a license, it's no. And I think Experts Exchange has CC BY 40 or something similar. I don't recall, but it's actually on their webpage. So everything on Experts Exchange is under a specific license, and you can only use it if you follow those license demands. And that goes with all code you find. And the book here that I'm showing you, Numerical Recipes in Fortran. You also have the book Numerical Recipes in C and so on. That's a terrible book. This book has numerical recipes, and you're not allowed to use any of the code of the book in your commercial software or your educational software without paying a license fee. So this is like an advertisement pamphlet, right? This is an advertisement of computer code, and you can additionally buy the computer code, but you first have to buy the book, which is the advertisement, and then you can buy the code as well. So I think this is just a perfect example of how you shouldn't do licensing. Think about this also when you write code and release it on GitHub. I try to be good and make sure that my code is with a license, which typically means GPL in my case. That's what I like to use, but I can also use MIT or BSD. And that gives the rest of the open source community a right to use what I do and make it better. So there's a whole range of licenses that we can use, and this is really important to know about. I've been involved in removing source code from large programs because they were copied from this book. So I found code which was copied from this book. I found code which has been copied from online sources where we don't have the license. And it's really important because this is what your company can get sued for. So make sure that you use things that are allowed. Make sure you follow the license terms. Okay, so those were the best practices things that I wanted to mention for you. It's a set of like 15 or so tips and hints. And I think these will give you a huge payoff. It's kind of like pay now or pay later. If you follow these guidelines, there is a cost. It's going to take you more time to do your work, right? If you're doing a mandatory assignment, it's going to take more time if you use testing, and more time if you use GitHub and source code versioning and so on. But at the other end, you save your time when you have a bug. You save your time when you have to figure out why it worked yesterday and doesn't work today, because then you have the tools to actually address that problem. So you can either pay now by doing it thoroughly, or pay later by paying the price where you were kind of doing things sketchily without a safety net and things go wrong. Does that sound reasonable to you guys?
Yes.
So yeah, I try to be good, but as you, sometimes I cheat as well, and I get really frustrated when my cheating comes back and I have to pay for the cheating by just looking through things and spending endless amounts of hours just tracking back what I did. Okay, those were the slides for that session, which for me was really important to share with you. The next thing I want to do with you is, now we have about 25 minutes, and what I want to do until then is have an introduction to hyperbolic conservation laws. So now we've gone through the computing pi example with the optimization, sort of finished that off. We did the best practices, and now I want to do the introduction to hyperbolic conservation laws. And then after the break, which is about 6 o'clock, I want us to start coding. Have all of you been able to either get access to Elex, which Jose has set up, or set up the requirements which is on the webpage of the course? So this is the software installation. Can I get a thumbs up from those of you who have access to Jupyter notebooks with PyCuda?
Yes, I set up all the environment and it seems to work.
Excellent. Thank you, Alfonso. What about the rest of you? Luis Miguel, did you have it working with Elex?
Yeah.
Excellent. What about the rest of you?
I didn't manage to get it work, but with Alfonso by my side on the same desk, so so I will write code, but I will just need to send it.
I think that's perfect, Daniele.
But
You
but
and
in the
Alfonso.
meantime, I'm trying to get it work.
Yeah, but I think if Alfonso has it working and you can sit together with him, that's just perfect because
Yeah,
working in
he's,
pairs like this is also always good.
Yeah, he's here. Then at the same desk. So,
Good. What about you, Pedro?
Me neither can get it work, but I'm solving problems.
Okay.
So in the future, I think that I could.
Now,
make it work.
if you cannot get it to work now, that's going to be completely fine. Just try to follow along with the things that I do and try to understand them and be active. What about you, Adrian?
Everything okay.
Ah,
No problem.
Excellent, excellent. And you, Jose Model?
I don't know English. Difficult to follow the class. I don't know exactly what is the exercise or what. I don't know.
Hopefully, you'll be able to follow the source code that I'm writing, and things will be a bit clearer there. And Jose Manuel, if you think that I speak too quickly or you don't understand, please let me know. I'd be happy to try to speak more clearly. Okay?
Okay, but don't worry. I can see the class again. It's better.
Excellent. Good. I'm really happy that you're here, by the way. Okay, so let me open the slides that I want to go through with this.
Maybe if you can share again the URL, because I think that Jose Manuel didn't come yesterday. So it would be great if he can follow at least the comments.
Yes. So I can share this here. Was that the URL you were thinking about?
Yep.
Yep. Good. Yes. So I don't have too many slides, but we're gonna do. I think, yeah, we can do this in like 20 minutes. And okay. Right. So in this, this is again a bit of slides. I apologize for that. I'll try to make it interactive as well. But unfortunately, you have some. I'm going to PowerPoint you to death today. In this session, I want to go through hyperbolic conservation laws, and I'll go through some explicit stencils for simulation of PDEs. And then we're going to go through a bit on partial differential equations on GPUs. So PDEs, that's partial differential equations. Right. The heat equation, that's like the prototypical partial differential equation. And I'm assuming that many of you don't really know what a partial differential equation is. So can I, just a quick round around the table. Do you all know about partial differential equations, or is that a new term?
We know them, but we did just like 4 years ago.
Yep. And I'm assuming perhaps some of you don't really remember these things too well. It's a long time ago and so on. Okay, but this is the essence. Okay, we have, if you remember back from high school, you would have something like an f of x, and then you could look at the rate of change. So you could see that, well, here the function. My pen doesn't work. In this section, the function is rising, right? In this section, the function is going down, and about here, the function is flat, right? So we had this rate of change. So we had f prime of x, that's the derivative of f of x, which is the rate of change. Which means that up here, for this one, f derived of x is greater than 0, right? It's a positive rate of change. The function goes up. At this point, f derivative of f of x is equal to 0. We have just a flat slope. And then in this section, we have f of x, the derivative of f of x is less than 0. Okay? Because it's going down. That's the basic building block. In one dimension, we just call it the derivative. But if we have two dimensions, something like x, y, z, then we could have a function which goes something like this. And let me see, it's going to be somewhere there. Okay. Right, so that's supposed to be like a three-dimensional drawing. Now here we can look at the rate of change, but it's difficult to say the rate of change, right? Because what's the rate of change? Here it was 0, less than 0, and less than 0, and more than 0. But for this in two dimensions, it's a bit more difficult. So we can talk about the local rate of change along an axis. So here, for this one, we look at the rate of change. Let's call this function g of x. Right? So there's just a g of xy. Sorry. It's a function of two variables, x and y. We can write down the rate of change along the x-axis. So that we can write like the partial, that's this strange d, of g of x, y, of partial x. That's the rate of change along the x-axis. And the same way we can write the, try a different color, right? We can write the partial derivative of x with respect to y, the y dimension. So that goes along the y dimension, right? So I put down the x dimension here and the y dimension there. Now the cool thing about this is that at some point we figured out that we could write physics using these mathematical terms. We could describe nature using rate of change along different axes. So typical things that we will see is that we have a function which is, it's not only in x and y, which is like this, but it's perhaps also in time. So it changes in time. So that can be temperature, it can be water. So think of this like a water surface, right? We can look at the change of the rate of change for the water surface, but also in time. So often we may get something which is on this form, g of x, y, t, the partial derivative with respect to x and the partial derivative of g with respect to y. And also the partial derivative. I'm happy that I have slides now because my handwriting is so poor. It's much easier to see the right notation in my slides. Partial derivative with respect to time. Time, x-axis, and the y-axis. So these are just the building blocks that we are going to use in today's lecture. By using these three and also the second order derivatives, so basically the rate of change of the rate of change, we can write up some physical laws. And these physical laws can be temperature, in a metal bar. Now, if I have a metal bar which is extremely hot in one end and then is cold in the rest, and we'll let time go, it's going to change. The warmth here is going to leak over, and we're going to get some sort of smooth transition of the temperature. So at some point we're going to get something which is perhaps something like this, where I'm trying to get the transition from hot to cold. Alright, so it's very hot here and very cold over here. And you have the transition. So it goes from warm to cold. So this is the change in time. Okay. That's the basics. We have these types of derivatives, which just comes from the regular derivative you remember. And using those, we can write up the laws of nature, which describe, for example, heat distribution, water displacement, and so on, which we then can formulate something like this with. So, going back, this is exactly what we've done here. So this formula up here, that's the partial derivative of u with respect to time, and u here is the temperature of the metal bar. And that's related to kappa multiplied by the second order partial derivative of u with respect to time, with respect to space. So you're just relating a rate of change in space with a rate of change in time, and from that you get a physical law of nature. Okay, so far I'm assuming you're thinking, well, that's not too interesting. Give me something that's a bit more useful. Well, the cool thing about this is that we can solve it on a computer. This is how we can go with a so-called explicit scheme. I want to go back to the drawing board. Here, okay. We had these three here. Let's skip back a couple of stages till we had this rate of change. This here. I want to continue with this one and just recall what this actually means. And fear not, we're going to get to the computing part of this, but I think we should get some of the theory into our mind first. So what we start off with is that we have, and I'm going to zoom in quite a bit, something like this. So this here is f of x. Okay, and we know what the derivative is. It's the f prime of x. But the definition essentially goes something like this. Okay, so I select 2 points, x0 and x1, and then I connect them through a straight line. So this up here, that's f of x0, and this up here, that's f of x1. And the distance between them has multiple different names, but let's call it delta x. A small change in x. Okay? That gives us this point here, f of x1, that's actually equal to f of x0 plus delta x. Okay, so we pick a point, x0, we go some step to the right along the x-axis, delta x long, and go up to the function again. And if you see these, if this point here goes towards x0, like if x1 and if x0 they meet, then you see that this line here, that should be closer and closer to the derivative. So this is actually how the derivatives formulated mathematically. So we have f derivative of x is equal to the limit of delta x goes to 0. That basically just says that this one is going to be very small. So we're moving this point closer and closer of, and we look at the thing here, the rate of change, that's f of x plus x0 plus delta x minus f of x over delta x. This is just the rate of change, right? And we cannot really solve this for delta x equal to 0 because this number up here, over there, you get infinity, right? But that's the definition. We take the limit of delta x goes to 0. Okay, I've spent some time on this, explaining this to you now, and it's not to waste your time. What we do in computers is that we say, well, let's drop the limit here, and let's just say that, well, f derivative of x is approximated by f of x 0 plus, oh, it's going to be of x0, right? I could drop the 0 there and just call it x, but let's keep the 0. F of x0 plus delta x minus f of x over delta x. Okay, so then I say that, well, delta x is a size. What this actually means is that I'm transforming my graph, which is continuous, into something which is discrete. So my graph now, through this formulation, goes to something which is a bit like this. It's hopefully going to be close to the same graph. And then for this one, I say that the difference between these is delta x, right? So I'm just imposing a discrete mesh on my continuous variable. And then I'm saying that, well, if this mesh is fine enough, I'm going to solve the true derivative, which is what we're trying to do to solve the actual physical problem. But I know it's not going to be, delta x is not going to go to 0. But it's going to be a small finite number. But if this is small enough, then it's going to be good enough. And that's really, really cool. And that's what I've been spending a lot of time researching on. And that's what's shown on this, this graph over here, actually. So in this graph here, you see that I've imposed a space discretization from x0 to x6. And also the same in time. So you can have a discretization in time. You're not working with continuous variables anymore. You're working with discrete variables. And the very cool thing is that the if I just show you again this this document camera, this function here, this gives rise to the formula that we're seeing seeing on the slides right now. So this slide set up here comes directly from that formula. So by taking that formula, applying it to these continuous variables, so I'm taking the continuous variables here, imposing the discrete grid, and using the discrete discrete derivative, then I can get this explicit formula. Okay, I've spoken a lot, like 5 minutes about this now, or more. And that's because it's really important. If I have this formula here, I can solve the heat equation on this numerical grid. And that's one thing that we're going to do later today when we're all looking at it interactively. So let's see how we can do this in Python, right? This here comes up as the formula, and I'll leave it as an exercise for you guys to check that is right. It's just plugging in the numbers and plugging in the discrete derivative I gave you. But this one, we can plug directly into the computer. We couldn't plug this one into the computer. We cannot solve this one. So the cool thing is going through the discrete mesh means that we can get something we can solve. And even cooler, we can solve it in parallel, because each single UI here can be solved independently of the other ones. If I go back to the slides here, that means that for each point here, this is U0, U1, U2, U3, U4, and U5. I have an explicit equation for each of them to evolve them in time so that we get the temperature distribution in the future. And that's the thing that I showed up here. So we can do this by plugging it in. We import NumPy, we set some initial conditions. We have something called a time discretization limitation, a CFL condition. It's a bit, let's just acknowledge that we cannot take an infinite amount of time when we're simulating. We have to take smaller time steps. It comes from this equation here. But then we can loop through time steps. And we can say that, well, the new temperature, U1, is related to the old temperature, U0, calculated like this. And this here function comes directly from the mathematics here. The final thing we need to add to this thing to make it work in practice is boundary conditions. And boundary conditions is shown over here. And in our case, we've just set that, well, the temperature at the end of the rod. So if we go back to my slides here, the temperature at U0 is going to be fixed. So it's always going to be the same temperature. So this is temperature going up in the y dimension, and space going along the x dimension. So U1 is going to be fixed, and U5 is fixed. So we just keep the temperature at those points, and we figure out, well, how does the temperature inside change over time? Okay, and then technically we just swap some variables, because if you look at this formulation here, I'm using UI minus 1, UN, the superscript n, and the U superscript n plus 1. So I need two time steps, the old temperatures and the new temperatures. So that's always what I'm computing here in this section here, and with the boundary conditions. And then once I have the new temperatures, I say that the new temperatures are the old temperatures, and the old ones, those are going to be the new ones. So that I calculate the new ones again. So by doing that, I can just go through using the same memory all the time and calculate the solution going forward in time. And that's going to give results like this. So this is something that we're going to do after the break. We're all going to try to make this work first in Python and then hopefully in PyCuda. And it's going to start off with some random temperatures, which is the blue line. And as time goes on, it gets smoother and smoother and smoother, as you would expect. So by going forward in time, this is exactly what happens. So this is laws of physics. So this seems to be correct, what I would expect. Okay. I'm going to skip this part here. And the final thing I want to mention for you is that the heat equation is kind of boring. It's in one dimension, and it's kind of boring looking at temperatures. We can do this in 2 dimensions by extending the variables. So I've already shown you like the partial differential, the partial derivatives, and here we see them in time, in x, and in y. And this is essentially the same equation as you saw earlier for the heat equation. But the cool thing for me is that we can go from the heat equation into the linear wave equation by just changing some small parts of the mathematical formulation. It looks almost identical. So this up here, that's actually the 2D wave equation. What's the difference between this one and this one? Okay, so spend 10 seconds looking at this one, and then I'm going to show you the next one, and I want to get some comments on what's the difference between these two. So here we have the partial derivative of u over, with respect to time is equal to kappa multiplied by the second order partial derivative of u with respect to x plus the second order derivative of u with respect to y. And here we have the 2D heat equation, wave equation, which gives rise to acoustic waves. So we go from heat to acoustic waves.
The constant.
The constant, it used to be kappa, and now it's c. That's one change.
And the second order derivative.
And the second order derivative on the left-hand side, right?
Yes.
If you look at this one, the c or kappa, you can change. It's I could plug in 5 in both, and then you wouldn't see a difference. Or I could call both kappa. So like traditionally, just call it c for the acoustic equation and kappa for the heat equation. But essentially, it's the same. Inside the parenthesis, it's identical, but the left-hand side goes from a first-order derivative to the second-order derivative. And then you go from something boring, which is heat equation, to something really exciting, which gives you waves. And that's something that I want to do with you also today. Okay, so I'm going to skip this as well. We'll come back a bit to this later on with the index, array indexing and so on. But most of the next session I want to spend interactively coding with you guys. So now it's 6:05. I suggest we take a break, but before that I want to ask if there's any questions so far.
Yes, I have a question. So we are calculating the derivative in each point in which we have divided the intervals, right?
Yes.
Perfect.
So we, if I go back to my my document camera here, for each point we calculate the derivative. So u1 has some derivatives, u2, u3, u4, and you see it changes, right? It's not the same derivative all this places, and we plug these numbers into this explicit formula, which is here. So this is a more complex explicit formula, but it's essentially the same. And from that we get some simulation results. Other questions before we take a break?
And for the 3 dimension, do we need to do like the third derivative of the equation?
Excellent question. We could look at this, right? For the heat equation, you see this formulation up here. This top formulation doesn't specify the number of dimensions. So actually this can mean that I can have 1 dimension, 2 dimensions, 3 dimensions, and so on. So it's very easy to say that this extends easily to 3 dimensions. So for most of these, they do extend to 3 dimensions. And I have some simulation results, which I may show you later on in 3 dimensions. But there you have the partial derivative of u with respect to z, like the third spatial dimension. Okay, I think we all deserve a 15-minute break. So I suggest that we meet in 15 minutes, so that's 8:20. Okay?
Okay.
Great.
Great. I'll see you 8:20. Bye.
Bye. Okay. See you in a bit.
Like,
Welcome back, everyone. Are you all here?
Yes.
Excellent.
Yes.
Good to hear. So, as I said, we did this thing about the derivatives, the partial derivatives, and then we went through a bit of source code thing where we said that the derivatives could model physics, and because we did it discretely, not continuously, we could plug it into the computer. There's a lot of things I hid from you when I went through that. So there are some footnotes in the margin that I should have mentioned, but we don't have time for. Okay, so there's more to the story, but let's continue because I want to do something fun. And now I want to go through the heat equation example first, which is this thing about this metal bar here, where we start off with heat in one end, cool in the rest, and we get something which has a transition. And I want to first do it in Python and then continue to do it in PyCuda. So let's just start off. I think most of you have the possibility to run a Jupyter notebook for yourself. So please try to follow along and do what I do. Do it interactively, but there is a chance that you will get some mistakes. Let's say you get some errors in your Python code, missing a tab so that you have the wrong indentation and so on. Then suddenly you fall off. If you fall off and I think you will get less out of the lecture if you keep bug fixing your own code instead of trying to follow what I'm doing. So I will try to take it at a slow pace so that we can all try to do it together, because this is going to help you in your exercise, the mandatory exercise in the course. But keep it in mind, if something goes really wrong, perhaps it's better to follow what I do and just watch instead of trying to do it yourself and bug fixing. Because for me at least, trying to fix my own code while someone else is talking is really difficult. I can only focus on one of them at a time. Okay, let me see where I was. I was there. Okay, we were here in our Jupyter notebooks, and I would like you all to just start a new notebook. So hopefully you will have something which looks like this, and you could go into new file and call a new launcher. And then from the new launcher, you want to select a notebook, and from the notebook you want to select the GPU env. In my setup, unfortunately, it's called GPU dev, but it's the same thing. So call that one. And if you don't select this one, you may not get the right results. So let's select this one and try. The first thing I want you to do is print hello world. And the next thing I want you to do is import PyCuda. Hopefully it should look like this. So I'm going to give you a bit of time to just get this up and running. So can you let me know if this works for you? Because I think everyone except Jose Manuel should be able to do it either in pairs or individually.
Yes, it works even if I don't have when I start a new notebook, the GPU dev, I only have Python 3 IP kernel.
Perfect. Yeah, so you had only this Python 3 IP kernel. Yeah. Luis Miguel, does it work for you?
Yep.
Perfect. What about you, Pedro?
Yes, this is working.
I'm really happy. Adrian.
Yes, it's perfect.
Excellent. And Jose Manuel, please let me know if there's something you're missing as well.
I can't create a notebook Jupyter. I don't know why.
Yeah, but hopefully that's going to be worked out offline, sort of after the classes. But hopefully it's going to be interesting for you as well. Okay, I will start off with the heat equation in one dimension, and to do that, I don't have the right one here. The heat equation. Let's start off with importing the right packages. So we imported PyCuda, and we also want to import the driver. Import PyCuda driver as CUDA. And import PyCuda compiler dot source from PyCuda compiler import source module. So this should give us the required packages from PyCuda, but the last thing we also need, that is to import the auto init. And I'm going to cheat and get the thing from here. So import PyCuda auto init. With these three entered in like that, you should be able to be good to go. You should have something which has Python and CUDA packages imported. We also want to import NumPy, because that's one thing we're going to use, and also matplotlib. So import NumPy as NP, and import matplotlib .pyplot as PLT. And actually, I'm gonna copy these things into the chat, so that you can just copy it into your source folder if it doesn't work. There. It's a bit easier. Okay, now what we wanted to do is to create the heat equation, right? And the cool thing here is that if I'm in this new cell, I can change it from code to something called Markdown. And Markdown is very handy in working with Jupyter notebooks. So I can write something like heat equation. We are going to solve the heat equation, which is, and then I'm going to do so this is the first one, and then it's going to be parcel u. So I'm writing down it's just kappa. Like this. Okay, so I'm writing something very strange. This is LaTeX for those of you who have heard about it before. I can shift enter and it displays the nice mathematics. And I think that's really, really cool, right? So it just gives me directly into my Python code some mathematical notation with some headings and stuff like that. So that's very, very neat, especially when you're working with something you want to show to someone else. You can just copy your equations in, you can copy your thoughts and drafts, have numbered lists and so on. But let's continue with this one. We need to do the following. Okay, numbered list. I don't remember numbered list in Markdown. I'm just going to do a list. So number one, I think is create variables u0 and u1. Now these were the two time steps. U0 is the old temperatures. U1 are the new temperatures. Okay, U0 are the old temperatures, U1 are the new temperatures. So that's the first one. We need to create the variables. Then we need to initialize the original temperature. Okay, so we'll just initialize this metal bar that we're holding, right? And we'll say it's going to be warm in one end, it's cold in the other end, and then we'll see how it works. But you also need to say what the temperature is inside the metal bar. And then, after we've done that, in a for loop, solve the heat equation one time step at a time. Okay? And in that for step, in that for loop, what we do is that we have the new temperatures based on the old temperatures, right? And then when we're done with the for loop, we swap these two so that the old temperatures, or the recently computed ones, are the input to the new temperatures. We compute a new time step and we swap these again. So every other one we swap U1 and U0. So that's what we're doing. And then plot every plot after X time steps, right? And there we have it. Now we have already documented what we're going to do, and it's easier for me already now to see the solution here, or to work with developing the code. Okay, the next thing I want to do is to create a function, or we can actually do it without a function to begin with. It's easier to start without a function. Now let's start with a function. Def heat equation. And let's just call it U0. So U0 here, that's our initial temperatures. Okay? So let's just make things easy for ourselves so we get a skeleton up and running and do the plotting. And then we can do plt plots U0. That's all we do. Okay? But if we execute this now, nothing's going to happen because we're not calling the function. So what I suggest we do is that we initialize a U0. We create in an array with initial temperatures and then call the function with it. And creating this first variable we can do by simply calling it with numpy. So U0 is equal to, or initial temp, to distinguish it from this U0 here. So it's a best practice to not use the same variable name inside and outside the function. You remember from last night I actually did a mistake because I used almost the same variable name inside the function and outside the function. So I made a mistake there. But initial temperature is numpy. Let's do some random temperatures. And let's just do 10. That's easy to work with. And then heat equation initial temp. Okay. I execute it and I get something which looks like this. Okay. I'd like you to let me know when you have the same you're not going to have the exact same temperatures because yours is going to be a different set of random numbers. We can actually do that random seed 42. If you do the exact same as me, I think you're going to get the exact same function that I have by adding this here. But please let me know when you have the graph up and running with your local version.
Yeah, I heard.
Perfect, Luis Miguel. I can also copy paste this into the chat so you can have it there. Then it's a bit easier to work with. And if any of you are struggling, let me know. And I can possibly see what's possibly help you.
I just had like an error importing PyCuda that driver, and it tells me that win error. It's not an application, but a valid application. I think I'm gonna resolve it after the class.
Ah, yeah. So maybe then you and Daniel cannot do the PyCuda stuff because you're sitting on Windows, right?
Yes, exactly.
Yeah. So I think this, yeah, you need to debug some stuff with PyCuda on Windows to make it work. Yeah. So do that after class and try to, yeah, contribute to what I'm doing instead would be good. What about you, Adrian and Pedro?
It works.
Good.
Yes, done.
Excellent. Then I can continue. Okay. So far, we just initialized, we plotted something. And the list here, what I was supposed to do, helps me a lot. Okay? Create variables u0 and u1. Okay, so that already helps me now. So u0, we have u0 initial temperatures. Need to make space for u1. And then we can use empty like. So u1 is equal to numpy empty like u0. Like u0. Okay? And then we can plot u0, u1. And I'm going to differentiate these. So I'm going to plot u0 with r dashes dot dash. I think that works. And the other one with x's. And it's going to be blue x's. Okay, so now I'm going to get dots with a line for the u0. And I can label them as well. Label and then PLT legend. Okay, I execute this, and hopefully I'll get a graph with the two graphs which are identical. Ah, they're not supposed to be identical. The one is empty, right? U1 is empty. But it gives you something like this. And you don't have to have the label and stuff. That's just for making it prettier for me. But this was what I did.
Maybe adding the dash in the blue one so we can see the variability of the one.
Yeah, we can have the dash there as well. I think we can do something like this. So it's double dashed. Then it's easy to see the difference. So this, it's very easy to see things and plot. Thank you for the good suggestion. Okay, so I think I'll copy this again to the chat, so you have it. If you've made some mistake and are stuck, and I'll just continue a bit. Okay, let's look again what we did. Create the variables, initialize the original temperature. We've done both of those. In a for loop, solve the heat equation one time step at a time. Okay, for loop. Let's add another variable here, num time steps. And then we'll add that again here. Time steps is equal to, let's say, 10. let's just do 1 to begin with. Then it's a bit easier to debug if you're just doing a single time step. So if I was really tempted to do 10 because it's a small number, but if I do something wrong, it's very difficult to see what's gone wrong after 10 iterations. So just keep this one at 1, and we should still just have the same plot. But the next thing we need to do is to add the for loop. So for I, or let's do n, right? If we go back to our notation here, let's see. This was the notation, right? There. And I was using n and n plus 1 as the time steps. So n was the time index, and I was the space index. So let's try to use the same here. We use n as the time index and I as the space index. For n in range, num time steps. And then what I'm going to do? Well, I'm going to compute U1 from U0. All right, compute the new temperatures from the old temperatures. And then I'm going to do swap the old, new and old temperatures. And the last one is very easy. U0, U1 is equal to U1, U0. And now we're just stuck with computing U1 from U0. Let's see how we can do that. We had this formula up here. This one here. I actually had that in one of my slides. So I will copy this, and this is a bit cheating for you. So I'm gonna just have it in the as a comment, and I'll comment it on it as we go. Okay. For this one, this came just from the mathematics. We had the continuous derivatives, which we transferred into the discrete derivatives, and then we replaced the mathematical ui of n with u0 of I. This variable here, right? But here you see one thing. I'm using the spatial index I because I have to do this equation for all the different places in space. Right? If I go back to this this drawing that I had, right? This one here, I have to solve the equation for each and every one, right? So I have one for loop which runs in time, which goes forward in time, and I have to have another for loop which goes through all of these points in space. Now you could argue that I could do this in vectorized notation, as I said earlier, right? With the Monte Carlo simulation, that, well, if we do it vectorized, it's far more efficient. Let's not do this now, because that's going to waste time that we don't have. I would rather focus on getting the GPU version up and running. So let's just do a for loop also in space, right? So here, first a for loop for the time dimension. And then down here, a for loop for the space dimension. For I in range. And now, what's the space dimension? Well, let's start off with finding the number of cells. We can do that. Num cells is equal to u0 dot oh, I don't remember. I think it's size. I don't actually remember. I'll have to come back to this. This is
What do you want to calculate?
the number of points inside U0. So it's dot shape of 0. I think this is the number of cells.
Yeah.
Sorry, I am. You know when you're coding and you're suddenly forgetting all of the things, especially when you're in front of the camera. But I think this is roughly right. So this find out how many cells there are in U0. How many numbers? Okay. And then I'm not going to do anything with the numbers yet. So I'll just write pass here. And I'll see if things work. Okay, because now I've written quite a bit of code. And I want to check that it at least compiles. So let me do Shift Enter. And good. It does compile at least. Okay. So what we've done so far, we expanded our heat equation function with taking the initial temperatures and also the number of time steps we want to execute. First thing we do is we create the initial temperatures. Next thing we do is find out how many cells do we have. Next one, we loop through the number of time steps. So we're going to solve one time step at a time. And for every time step, we're doing the swapping of the two variables, right? And this is important when we get to the GPU because we're going to do this exact same there. And then we loop through all the cells internally, okay? And then we swap the ones, as I said, and we plot. Okay, now I want to do this because this should be just plug and play as I do it like this. And I want to ask you, what's the problem with this? What's the big issue with doing this? Look at this line, which I'm highlighting here, and try to reason. What's the problem that we're going to reach into? You can look at these line above as well. And I'll give you a further hint. What happens if I is 0?
So in where you are trying to access -1, it's part of the code.
This is a huge issue, right? If u of 0 of I minus 1, I is 0, so that's -1. That's not right. And the same, if I is equal to the last element in the array, then I plus 1 is outside. So let's look at this expression here and see what it actually means. So let's go back to this one, right? Okay, what we have in the heat equation, we have this central, this second order difference, right? Now, what we did with the, let me see if I can find my, didn't I write this up somewhere? Okay, I didn't write it up. We have the second order difference, right? So we had the partial derivative of x with respect to the partial derivative of u with respect to space, the second order. And what we're actually doing there is that we're creating a central difference. What we did with the first one, the partial derivative of u with respect to x, we created a forward difference. And what this means is that, well, the forward difference, I'm looking at f of x0 and f of x1. I'm looking forward, okay? I could actually be looking backwards as well. There's nothing wrong in that, but I was looking forward. So the central difference, that looks both forward and backwards. So creating the central difference, it actually takes 3 points. It has 1 point. It looks at these 3 points to compute the value of UI. So it uses UI minus 1, and UI plus 1. It uses these 3, whilst the forward difference we were using, that only uses 2 points. UI and UI plus 1. Only those 2. What this means, if I take this one, looking at 3 points, that gives rise to this minus 1, I and I plus 1. If I take this stencil of these 3 points, that works very well if I do it here. Let me try a different color. It works very well if I do these 3 points to create the central difference for this point here, right? Because I have all 3 points. But if I take the point here and want to create the central difference, I have a big problem here. This is a big problem, right? Big no-no, because I don't have that value. And the same up here at the right-hand side. If I want to compute the central difference for this point here, I have to use U4, U5, and U6, which doesn't exist, right? And this is where boundary conditions come in. If you remember, I was talking about this, putting the temperature as fixed at the endpoints. What we actually do now is that we say, well, let's not solve the equation for the last points. Let's just say that the temperature here at the last point is going to be fixed. By fixing those 2 endpoints, we can move the stencil for all the other internal points. And then it works. There are multiple ways of doing boundary conditions, and boundary conditions is something you can do a full PhD on, okay? So that's a huge topic, and one of the most difficult ones. But let's just jump over it and use some simple boundary conditions that we know work. Okay, so that means that we're not going to go to num cells. We're going to start with 1 to num cells minus 1 and solve the equation there. So a for loop for the space dimension, loop over all internal cells, the ones except for the endpoints. And then I want to add the boundary conditions. Set boundary conditions.
If in reality we are calculating like 3 points, why don't we use an increment of 3 so we don't recalculate again the same values?
Ah, good question. So what we're doing here is that we're creating 1 value, but we're reading 3. So if I go back to the document camera, thank you for asking. What I'm doing is I'm taking these 3 points here, these 3 temperatures, and they will give rise to the temperature in the next time step for this one. So I'm reading off these values, the 3 values there, and I'm calculating this one. So to do calculate the neighbor one, I have to do 3 other ones. I have to do these 3. Let me do green. So for this one, I have to do these 3. So actually, even though I have to do it for every single point here, right? Every internal point. So I have to do it for this one, this one, this one, and this one, the 4 internal points, and let the end ones be fixed. But for every internal point, I read 3 of the existing values. Okay? So now we have the doing it for all the internal cells and then setting the boundary conditions. And then I'm just going to say that u1 of 0 is equal to u0 of 0. Okay? And u1 of num cells minus 1 is equal to u0 of num cells minus 1. And I think in Python you could just use minus 1 there to get the last element, but this is kind of like C indexing. And now, hopefully this will actually work. So let me try to run the code first and then copy it to you if it works. Oh, it doesn't work. Kappa is not defined. Okay, this was good. We forgot something in the equation. This kappa here is something that we need to have in here. So we need kappa and we need dt as well, the time step. The time step comes in there, and we also need the dx. So this is the discretization in time, and this is the discretization in space. So let's just add some numbers for that. Let's say that kappa is equal to 1, dx is equal to 1, and dt is equal to 0.25. I think that works. Let's cross our fingers and hope it works. Shift enter. I've still forgotten something. Thank you, Luis Miguel. It was kappa, dx, dt. And now, this is very scary. Was it dx and dt, or was it dt and dx? I'm assuming that for a lot of code that I've written, I've spent days looking for bugs, which was that I did this instead of dt dx, because they're both floating point numbers, and it's very difficult to actually see what's going on there. So one thing that's possible to do is to name the arguments in Python. So kappa and dt and dx. So what I can do is I can say kappa is equal to kappa, dt is equal to dt, and dx is equal to dx. By saying it like this, and I can actually just say, I could skip these, and actually skip time steps as well. I'll just say time steps is equal to 1, kappa is equal to 1, dt is equal to 0.25, and dx is equal to 1. By doing it like that, it's very easy to see. And this is something Python supports. I can also do u0 equal. So these are named arguments. Let's try if this works. We got unexpected keyword argument time steps, because it's num time steps. Num time steps is equal to 1. And good. Something happened. Let me copy this source code to you guys so you can see it and see if it also works for you.
Although you are naming them while calling the function, you have to keep the order. You cannot put like the order you want.
Maybe I have to. Okay, so I cannot do this, for example. It seems to work.
Great.
So that's like a safety mechanism. There is, in Python you have different types of variables. You have named variables, and you have positional variables, and you have, or it's called keyword arguments and non-keyword arguments, and I don't remember the name of the last one, but there are different types, and there are rules on how you can mix these. But what I've done now seems to work well, and it will give me an error if I do this. Then it's going to say, no, this doesn't work. Positional argument follows keyword argument. So I have to do the num time steps. Okay. I'm actually seeing something that I'm expecting, but the graph is wrong. it's calling initial temperature for the updated temperature. And you can see that because I'm calling it U0 after I made the swap, right? So I made the swap over here, which means that I just updated U1 is the new temperatures, and then I swap it. So that U1 is now U0. So I have to plot U1 and U0 like this. And then I have the initial temperature and the updated temperature. And you see it actually goes much smoother, which is what you expect. And then I can start experimenting, running more time steps. Let's do 5 time steps. It goes much smoother. Let's do 50. It goes much, much smoother. Let me actually change one thing. Making the plot here. I'm going to move that. I'm going to change so that I return the value. Return the updated temperatures. Return U0. And then I can say U1 is equal to this. And then I can plot the temperatures U0 and U1 outside like this. And then actually to do this properly, yeah, I have to do, this is a technical Python thing, but I have to do a copy here so that I make a copy of the initial temperatures. And it's called initial temp, not U1. Okay. Let's go back to, let's say, 4 time steps. You see it gets smoother and smoother. And here's the source code for you guys. Okay. This was our first simulation. Now this is kind of boring because it's just a line which goes through there, but this would be a larger mandatory assignment when I was studying. We could do this in like half an hour with very good, or I wouldn't say very good, but with explanations going on over whilst doing it. So we're doing it at a relatively slow pace. Now what I want to do is move this over to the GPU. And the key thing here, and why I've spent so much time on this CPU version first, is that to make the parallel GPU version, it's much easier if we understand what we're doing first with the CPU version. And with the CPU version in place, we have something which we trust, right? This seems to work. We get what we expect. Okay, the thing here, number of time steps. Let me just copy this cell. I'm going to copy all of this source code, and then we're going to create the GPU version. So I'm going to copy this into a new cell, and I'm going to call it heat equation GPU. And it's going to be exactly the same. Okay. Initial temperatures, we need to make space for U1. This we need to make into GPU. So I'm going to run through the function now and mark down my comments on what I have to do to change. And then we'll change it one by one and see how we can get it to work. Make this move to GPU. Okay. Find out how many cells there are in U0. We can still do that on the CPU. Looping over the time steps, we still do that on the CPU. But then looping over all of the internal cells, that's what we move to the GPU. Because here, let's say we don't have 10 cells, but we have 100 million cells. If we have 100 million cells, then using the GPU, we can run all of those in parallel. And that's the beauty of this type of mathematics, that it's embarrassingly parallel and it works very well with the GPU. So we have to move this expression to the GPU to make it run faster. And the same with this set boundary conditions, move to GPU and swap the old and new temperatures. We can actually leave that on the CPU because we're just changing pointers in how we're calling the kernel. So we'll come back to that. And return the updated temperatures. One thing we actually need to do more, we need to also make U0 on the GPU and upload from CPU, right? That's one thing we need to do. And finally, we need to download from the GPU to the CPU. Download U0, new temperatures, from the CPU to the GPU. And other than that, it's supposed to be identical. So let me just change this function like so. And right now, if I execute it, it's going to be the exactly same because I haven't really done anything on the GPU yet. But we're going to start. Okay. I suggest we get the data movement going first. Just like we did with the Hello World PyCuda. So what I would like to do is to make the U0 on the GPU and upload it to this from the CPU. So U0 GPU is equal to CUDA mem alloc. Wasn't it mem alloc n bytes, and then it's U0 dot n bytes and U0. That's the number of bytes, and then CUDA mem copy host to device. So we're copying from the host to the device, and it's going to be U0, and the target is U0 GPU. The source is U0, like so. Okay. Now, a big important question to you. Do you remember what we had to do yesterday, which was really important about memory transfers? It has to do with the data type. U0 is now a double precision floating point array from NumPy. So we need to make sure it is single precision. So I'm going to write an assertion here. Assert U0 dtype is equal to NumPy float 32. And if that doesn't work, it's going to crash. So let me try executing it now and see what it says. Assertion error. It's not float 32. So let's fix this already now and say that, well, the initial types are going to be as type NumPy float 32. Okay? Because now we have floating point numbers, and the reason for using floating point numbers instead of or single precision floating point numbers instead of double precision is performance. For our case here, single precision is more than sufficient. It's going to be enough for us to do good simulations, and it's going to be much faster than running double precision. We can run double precision, but it's going to be slower. I run it. Good. Still though, it's still using the old stuff, but at least now I was able to upload some data to the GPU. So let me do U1. That's going to be the same. Oh, I'm sorry. That's going to be the same kind of calculation as this one. So I'm going to replace this one with U1 GPU is equal to CUDA mem alloc U0 bytes. Now I have both the U0 and U1 allocated on the GPU, and U0 has been initialized with the initial temperatures. Good.
But in that case, you have to move the assert before, right?
I don't have to, but I should. Yes. So let's do that as the first one, right? And why I say I don't have to is that this one doesn't actually upload any data. Right, so as long as I have it somewhere, it's going to be fine. But it's good practice to have it first. We're using single precision in our kernel. Okay, but I did get an error message here. It has no bytes because it's supposed to be n bytes. N bytes. And it's still U1 reference before assignment. Good. So what I did now is I made this U1 allocated. I renamed the U1 from the CPU version and called it GPU. And I have U0. But then I get an error, a big mistake here. All right. So in this one doesn't work anymore because right now I don't have U1. So now we need to create the CUDA kernel. So I would like to do that. We can do it in the same function. I'd like to do it up here. So kernel source and heat equation kernel source is equal to, and then the triple ticks, like so. That gives us a multi-line string in Python. And then we're going to use this traditional CUDA kernel. Global void heat equation 1D. And then we need to think about what kind of arguments this function is going to take in. Okay, I know a couple of them. It's going to have float star U1, float star U0. It has to have floats kappa, floats dx, floats dt. But it also should have unsigned int nx, the number of cells. Right? This is because when you're launching the kernel, you don't know how many threads you actually need to have within your domain. Right? So you could launch 512 threads, but let's say your domain was only 20. Then you don't want to run the cells which are, or the threads which are more than 20. Okay? So these are the variables that I'm using, and I can make it a bit easier to read if I do something like this. I don't know actually if it's easier to read, but for me those lists can be nicer. Okay, now you guys need to help me. What do I need inside my kernel? I know I'm going to do this this calculation here. All right, so I'll copy that one. I know I'm going to do this one. But what do I need? How do I calculate this one? Well, let's go through and see what we know here, okay? Do I know U1? Well, yes, U1 is a parameter which comes in. Do I know U0? Yes, it's a parameter that comes in. Kappa, yes, comes in. DT comes in here. DX, that comes in here. U0 we've already mentioned. And I'm not using this NX, but all the other parameters are actually being used. So what am I missing here? Can I write it like this, or is something wrong?
You have to replace I by the index.
I have to replace I with some index, right? Exactly. And I think many of you perhaps saw that. This I is not defined. So let's define it. So int I. Let's do int I is equal to, and then we can use the traditional CUDA indexing, right? Where we get the thread ID. And that's something like block index x multiplied by block dim x plus thread index x. Now we have the I. That's good. We have the index of our domain. And now we need to make sure that we get the boundary conditions as well. If I is equal to 0, first cell, boundary. So if I is equal to 0, then we just say that u of 1, u1 of I is equal to u0 of I. Excellent. And the same with the other boundary. If I is equal to nx minus 1, then we do u1 of I is equal to u0 of I. There. And else we do this stuff here. Now, I actually need to do else if I is less than nx. We have to check that. Because let's say it's, as I said, it was something outside of the 20 elements we had. So I could be like 500. Then we don't want to execute that one cell because that's going to give us a memory error. So I get this else if. So first cell boundary, last cell boundary, and then internal cells. And the kernel should be good to go. This is actually all that goes into the kernel. This should replace both the boundary conditions and the execution of the kernel. So let me try to run this as a source module. So module is equal to CUDA is equal to source module of kernel heat equation kernel source there, and then heat equation GPU is equal to module dot get, isn't it get function? I have to double check my my cheat sheet here. Get function, yes. And now remember, I have to do this heat equation 1D.
In the else if, it should be like nx minus 1.
Yes.
And in the previous if equals to nx.
No, this has to be nx minus 1 because we start with 0 indexing, right? So if this was Fortran indexing, this would be 1 and nx, right? Because that's the first cell is 1. But since we're using C indexing, it has to be 0 and nx minus 1. And you're completely right. This should be less than nx minus 1. But still, since it's an else if, it wouldn't really go into there. But it's a very good thing to note to make the code more precise. Thank you. Okay, but then we create the source module, we get the function, and then we should be hopefully good to go to call the function from our Python function down here. So let's try this, okay? Right, so here, instead of this one, we're gonna move it to the GPU, and also the boundary conditions. These are going to be moved to the GPU. So just the internal computation and the boundary conditions. I remove those and I'm going to replace it with the heat equation GPU. And then I need to remember all of these functions that it had. And this is where it gets really tricky. If you mess this up, change the order of the arguments here, there's never going to be an error message which helps you. So I'll copy those down to where I need them. Function arguments, which were float u1, u0, kappa, dx, dt, and x. Okay. So we want to do u1 GPU, u0 GPU, numpy float 32 of kappa. And note that since kappa is a variable already in Python, it's a double precision number. So I have to make sure it's made into a single precision number when I'm sending it. The same with dx, mp float 32 nx, dx, sorry, mp float 32 dt, and then np uint 32 of num cells. Let me move it up there so you can see what I'm writing. This should actually kernel function arguments. This should actually call the kernel. The only thing we're missing now is the block size and the grid size. So let's just create a block size. Block is equal to 512, 1. So it's going to be 512 cells. And then grid is equal to, and now yeah, I need to, okay, let's num cells divided by 512, 1. This is kind of bad because this is going to round down. So let's say I have 400 cells, then the grid is going to be 0 in this section here. So let me do numpy ceil of num cells divided by 512. Okay, so I'm launching at least. Ceil means that I'm moving up, right? So this is going to be, if this is 400 divided by 512, it's going to be like 0.8. Then it's going to ceil, which means move up to the next whole integer. Okay, then I swap the old and new temperatures, and this is really cool. U0 GPU, U1 GPU, U1 GPU, U0 GPU. This swap here doesn't copy any data. It just moves the pointers. So if I have my two arrays, which are stored in the GPU, U0 is going to point here, then there. Point there, point there, point there, point there. So it's a really efficient way of just swapping the data. So this has essentially no cost at all. The final thing we need to do is download. So I'll do that by creating a new variable. So it's u1 is equal to numpy empty like u0, the initial conditions, and then CUDA memcopy device to host, and it's going to end up in u1, and it's going to come from u1 GPU, and then return u1. Whew, that was a mouthful of code, right? Have any of you been able to follow along with the code that I've been writing? Or is it a bit...
Like on our, I told you just watching them.
Yeah.
Because even Alfonso didn't manage to get it work, but now it's working, but we didn't write all the code. So.
Excellent. So it's working for you now on Windows. I'm really good to hear. Glad to hear it. Good. But any of the rest of the gang here, have you been able to follow some of the code?
Some of them, yes, but not the C part.
Yeah, the kernel becomes a bit difficult, right?
Yeah, the thing is that I've been thinking why we are putting the conditions there instead of just initially setting the arrays with the fixed values.
Yeah, for these ones here, just initializing them fixed value.
Why don't do that?
We could do that. Initialize them as fixed values and never touch them again. That would be possible.
Mm-hmm.
Definitely.
Because in this case, we have to evaluate these conditions every time we execute the kernel.
Yes, you're completely right. But the good thing here is that this is not going to cost anything, because on the GPU you're working with these warps, so the thread is going to do something even though you're not asking it to do something. And because of the coalesced reads and writes, the memory is also going to be moving, even though you ask it not to move it. So the actual cost of doing these operations here is close to zero. So it's like a mental charge. This looks like it's doing what it's supposed to do. But let me now try, we don't have too many minutes left, but let me try to execute the cell. And hopefully I don't have too many mistakes so far. It does give me a mistake. Okay, no registered converter was able to produce C++ R value of type unsigned in from this Python object of type float64. Whew, not too good. So I think this comes from, let me just double check where it comes from. Yeah, so it comes from this thing here. And I think it may come from this grid, right? So this seal function here, let me just move this grid stuff outside. So let's move this. I'm gonna move the block and grid size up here. Okay. And then down here, I'm gonna just say block is equal to block, grid is equal to grid. Okay. And then I forgot to do the conversion from floats, because this ends up as a floating point value, and you could spend some time trying to figure out what it is when you haven't done this before. So int there. Now it becomes an integer number, and I think we should be okay. Let's cross our fingers. Still not good. Local variable numCell reference before assignment. Okay, so we didn't actually do it right. We have to move these ones after we get the numCells down here. Okay, try number 3. Whew, something happened. Is this, it looks, okay, now I'm suspicious because it gives the expected results. Let me see if I can change the kernel to something that I wouldn't expect, right? So let's say that for the internal ones, well, let's just say plus 0.1 for the boundary conditions, right? By doing that, I should see a change down here, that the endpoints should move. So that I'm actually running the code that I think I'm running. And at least the last one moved, the first one didn't. That's kind of strange. I think that's very strange. I think if I is equal to 0, I don't see the mistake. And it did change 2 values up here. So it changed 0.2. I don't see the mistake. But let's skip that. We're running out of time. I'll double check what I've possibly done wrong, and get back to you to see what I've done. But at least what we got here was something that ran the kernel, and it did run it for multiple time steps. So it did run 4 time steps in this one. So that was very good to see that it actually did run 4 time steps. It could run 10 time steps. Let's do 1,000 time steps. It runs really, really fast. Now, the thing that I mentioned about this Monte Carlo simulation, right? There I said that we ran the kernel only once, so using this prepared call that didn't make sense. In this case, we're running the kernel 1,000 times to create a single result. So we're uploading the data to the GPU, running 1,000 iterations there, and downloading the data back again. In this case, it's very important to make each kernel call as efficient as possible. So here it would make more sense to actually have the number of have the kernel with the prepared call instead of the way we're doing it now. But this showed that we could actually get something which is not too unsensible, at least, by running this. So I'll have to double check what's really going on with the last one there. But it's reasonable. Okay. We didn't reach the end goal for today, because the end goal for today was to do the heat equation in 2 dimensions, and then also the linear wave equation in multiple dimensions. So that is unfortunately left as an exercise for you guys. The good thing though, I have given you some good pointers. So if we go to the lectures here, on day 2 I will send you the link to the exercises. On day 2 there are some exercises, the homework, which you are supposed to do. And in this homework, you're supposed to do the heat equation in 1 dimension, which is what I'm going to give you now and what you've already started working with. You're also going to do the 2-dimensional heat equation and the 2-dimensional linear wave equation and write a report about this. The good thing about this is that if I hide myself here, there, you can go to this link here. If I open this one, and it actually has the solution. So you can look at the solution. Now I'm telling you this because I trust you. I want you to learn from this course. So it has the linear wave 2D, the heat equation 2D, and it's going to be really obvious if you just copy the solution there. But it's very good for you if you're stuck to look at the solution, because that's going to help you quite a bit. So heat equation here in 1D, that goes through more or less what we've done today. 2D moves from 1 dimension into 2 dimensions and tackles the issue of 2-dimensional indexing in CUDA. And then the linear wave 2D, that's mostly for show. It's going to give you a very nice visualization of a 2-dimensional wave, which goes through. I don't think the animation works here. Yeah, it's on GitHub, so it doesn't work the animation there. But you can run this kernel on your own Jupyter notebooks, and it should give you a very nice animation which shows this droplet which goes through a pool and sloshes back and forth. Okay, this has been a hectic 3 hours. We've gone through the Monte Carlo this morning, we started with the Monte Carlo, sort of finishing off that. Then we went into the best practices for scientific computing. Then we went into the hyperbolic conservation laws, and then we did the interactive session now with the coding. And I hope that you will be able to do your exercises by yourself. If you're stuck, please get in touch with me because I want to help you get them running. And also take a look at the videos from last year's lectures. So they're all from 2021. They're here all online, and also the video from day 1 or from yesterday is also made online in a separate page here, right? So everything from yesterday is here, and this video is also going to be put down there. Good. Are there any questions or comments?
Nothing apparent of. Thank you your time and for the thing you have taught us.
Yeah, just wanted to say thank you for these 2 lectures. They've been really interesting.
Yeah.
Thank you so much. I'm really happy to hear it. I hope this is interesting, and I hope that you will learn something by doing these exercises yourself. I think the most you learn is by doing this yourself and not from me teaching you. And that's what I've tried to do with some of these interactive coding today, that you follow along in a different pace than if I was just going to show you some results and some slides. Good. I think we'll just end it off there. Jose, do you want to say some concluding or final remarks?
Not. Thank you for your contribution to the course. Thank you very much, Andre.
Thank you again so much for inviting me. I really enjoy teaching this. I think it's a lot of fun, and I hope it's useful.
You are always welcome.
Very good to hear.
Of course. Okay. Thank you, everyone. We have several assignments to do. The idea is to work in 2 weeks in the tasks we have to finish. Professor Blocker and me will evaluate all your submissions. I hope you don't have many problems. Whatever problem you have, we are here to solve the problem. We have maintain another meeting using the same media. Okay. Good luck with the job and enjoy a lot. Okay.
Can we still using the ILEX machine for these 2 weeks?
Yes, of course. The
Okay.
ILEX machine is available for
And
you
also the HTML
during 1 month. Okay.
Okay.
Please change the password. Okay.
Okay. Okay. And the final assignment that we will have to do, it is going to be also handed in the next 2 weeks.
Yes, I'll send you in 1 day, not today. I'll send you the scheduling. Okay.
Okay. Great.
Okay. See you.
Thank you all
Bye.
for coming and coming to these lectures. It's been great having you here.
Okay. I hope to see you next year in Granada.
Oh, me too. I'm envious of your good weather.
Okay. Bye. Bye everyone.
Bye everyone.
Bye, thank you very much.
Thank you.